Hello everyone, I'm Zixuan Wang, a PhD student at UC San Diego, and I'm working with Professor Jishen Zhao and Professor Steven Swanson. Today I'm going to present our paper, Characterizing and Modeling Non-Volatile Memory Systems. In this project, we build a profiler and a simulator for non-volatile memory and open source them on GitHub. This work is published in Micro 2020 and recently selected as an IEEE Micro Topics. In this presentation, I will first introduce the background of this project. Then I will introduce Lens, a profiler we built to characterize the non-volatile memory systems. And then VAS, a cycle-level simulator that matches real non-volatile memory performance. And finally, the validation results of VAS. Now, let's start with the background and motivation. Non-volatile memory is a type of main memory that sits on memory bus and provides byte addressable access to CPU, just like traditional DRAM-based main memory. It also provides data persistence, so the data written into non-volatile memory can be recovered after system reboot. Intel Optane DIMM is the first commercially available non-volatile memory product, and we can buy it now. But when we are using this non-volatile memory product, we found some unexpected performance characteristics. For example, here's a performance comparison between DRAM and Optane DIMM. We observe that some workloads are slowed down more than the others. We want to find out the detailed reasons behind these performance variance. So, we want to use a simulator to understand the architecture-level behaviors, such as TLB miss or overhead inside non-volatile memory DIMM. But the problem is, the existing DRAM-based simulator and emulators are not accurate enough. We first compare the DRAM Sim2 and emulator to Optane DIMM and find their bandwidth and latency are not accurate enough. We then compare the DRAM-based emulator with Optane DIMM. We find that using emulator, cacheable write bandwidth is higher than non-temporal write, while using Optane DIMM, cacheable write bandwidth is lower than non-temporal write. This motivates us to build a new memory simulator. But can we build a non-volatile memory simulator that is constantly slower than DRAM? The answer is no. Here's an example. We perform pointer system test on Optane DIMM and PMAP, a DRAM-based non-volatile memory emulator. We find PMAP latency is stable, while Optane DIMM latency is not constantly slower than PMAP, which means the real non-volatile memory is not just a slower DRAM. It has complex controller designs, multi-level buffers, and unpublished DDRT protocol. So, to build an accurate memory simulator, we first need to know more architecture-level details. This motivates us to build a new memory profiler. In this project, we first built Lens, a low-level profiler for non-volatile memory system. It has carefully crafted micro-benchmarks that trigger specific hardware behaviors and discovers the complex microarchitecture design of non-volatile memory products. It also achieves low-noise profiling results. Based on Lens profiling results, we built VAS, a validated architectural non-volatile memory simulator. VAS performance is validated with Optane DIMM. It has verified DDR4 model for on-DIMM buffers and can be integrated to Gen5 for full system simulation. VAS provides a general non-volatile memory model that can be reconfigured to simulate other non-volatile memory products. Lens and VAS are now open sourced on GitHub. Here is a high-level overview of how these tools work. We first profile the non-volatile memory with our profiler, Lens, and find microarchitecture level observations. We then configure VAS based on these profiling results. And finally, VAS simulation is good to go. Now, let's take a look at Lens design and its profiling results. Lens framework is built as a Linux kernel module to reduce kernel and user space switching overhead. It contains micro benchmarks written in assembly code to maintain well-controlled memory access. It disables cache prefetching and uses non-temporal load and store instructions to bypass the cache. It also uses AVX 512 registers to emulate cache line granularity memory access. Let's raise micro benchmarks on non-volatile memory using single DIMM and multi-DIMM settings. These micro benchmarks discover the access latency, buffer size, write policy, and many other architecture level details. Let's first use a pointer tracing test to detect the undimmed buffer sizes and their access granularities. A pointer tracing test is a random-based memory access test. It divides a memory region into equal-sized blocks and accesses these blocks in random order. It uses sequential access within each block. Here's an overview of non-volatile memory system architecture. There are CPU cores and integrated memory controllers. According to Intel's public documentation, there's a write pending queue inside integrated memory controller, although we do not know its size. And there are non-volatile memory medias on the DIMM. That's all we know from publicly available information. Now, we use a pointer tracing access test with 64-byte blocks to discover the buffer sizes. As shown in this figure, the x-axis is access region size, and y-axis is latency per cache line. We measure the read and write latency separately. In this test, the read latency starts to increase from 16 kilobyte region size, which means there's a 16 kilobyte buffer overflows at this point. We denote it as L1 buffer. For the same reason, there's a 16 megabyte L2 buffer. The L2 buffer latency is about 100 nanoseconds, which means it's inside a DRAM. The write latency starts to increase with 4 kilobyte region size. This indicates a low store queue on non-volatile memory DIMM that performs request reordering and write combining. The write latency drops until 512 byte region size, which indicates the size of the write pending queue. Now we know the buffer sizes, but some buffers may not use the 64-byte entry size. To detect the buffer entry sizes, we still use the pointer tracing test, but in a different way. This time, we change the pointer tracing block size and measure the amplification factor in each buffer. Once the amplification factor drops to 1, that block size is considered as buffer entry size. The amplification factor is calculated as the ratio of the size of actually read-write data to the size of requested data. For example, if a 64-byte request reads 256 bytes into the buffer, then the amplification factor is 4. Here we use two examples to demonstrate how to detect the buffer entry sizes. In the first example here, we use a small block size, which is half of the L1 buffer entry size. And the memory region is divided into 4 blocks, accessed in random order. For simplicity, we assume L1 buffer contains only one entry, and all entries are already stored in L2 buffer. Now, CPU starts to access the first block. The corresponding entry is loaded into L1 buffer and sequentially sent to the CPU cores. Then the second, the third, and the fourth block. After this test, the CPU accessed all 4 blocks, which is 2 L1 entry sized. But L1 buffer actually loads 4 entries. This leads to an amplification factor of 2. But when we use a large block size that is equal to L1 entry size, the amplification factor drops to 1. Here in this example, we have the same assumption as the last example. The only difference is the block size is doubled and memory region is divided into 2 blocks. Now, CPU accesses the first block, L1 buffer loads the entry, and sequentially sends it to the CPU. Then the second block. In this test, the CPU accesses 2 blocks, and L1 buffer loads 2 entries. This leads to an amplification factor of 1. Here we show a read amplification factor under different block sizes for L1 buffer and L2 buffer separately. We notice that the L1 buffer amplification factor drops to 1 with 256 byte blocks, which means the L1 buffer entry size is 256 byte. For the same reason, the L2 buffer entry size is 4 kilobyte. Here we present a write amplification factor for low store queue and write pending queue. The low store queue amplification drops to 1 with 256-byte block, which means it performs write combining that combines consecutive write access into one 256-byte request. This is to reduce the read modified write in L1 buffer. The write pending queue amplification drops to 1 with 512-byte block, which means the write pending queue size is 512 byte, and one unfetched instruction flushes the entire write pending queue. In summary, we find the size of write pending queue is 512 byte, and it uses 64-byte entry size. The low store queue size is 4 kilobyte and uses 64-byte entry size. There is a 16 kilobyte L1 buffer with 256-byte entries, and a 16 megabyte L2 buffer in DRAM with 4 kilobyte entries. Next, we use an override test to detect the wire leveling data migration details. This test repeatedly writes data to the same 256-byte memory block and measures the write latency of each 256-byte write. We find there are long-tail latencies every 4 megabyte write, which may be related to the wire leveling mechanism in non-volatile memory DIMM. Here is an example of how wire leveling works. The CPU repeatedly writes data to the same memory media location, and this area is getting wear out. Then the controller in non-volatile memory DIMM blocks the CPU write, and then migrates the data to another media area, and redirects the following CPU write to the new area. This is similar to the wire leveling on SSD devices. To detect the data migration block size for wire leveling, we perform override tests on different sized memory regions, and measures the frequency of the long-tail latency. Here we notice that the long-tail latency frequency drops to nearly 0 with a 64 kilobyte region size, which means the controller migrates 64 kilobyte data for each wire leveling. In summary, the override test finds the data migration for wire leveling or thermal control purpose. This migration happens every 4 megabyte write to the same memory location, and it migrates 64 kilobyte data every time. Here we use a sequential write to detect the multi-DIMM interleaving scheme for non-volatile memory. We perform sequential write with different region sizes and measure the total execution time under each region size. We test the single DIMM and 6-DIMM interleave settings. Here we notice the write to the interleave 6-DIMM shows a repeated latency trend every 4 kilobyte. This indicates that different 4 kilobyte pages are separated to different DIMMs. Now, let's take a look at WANS design. WANS is a cycle-level non-volatile memory simulator that is flexible and reconfigurable. It can execute memory traces and can be integrated to Gemfile or other cycle-level simulator for full system simulation. It is written in C++ 17 standard with a modularized software design. More importantly, it can be reconfigured using a simple configuration file without any change to source code. Here is an example of WANS non-volatile memory model. It has an on-DIMM low store queue that reorders requests and performs write combining. There's a read modified write buffer, which we refer to as L1 buffer in the previous slides. There's an address indirection table stored in on-DIMM DRAM that handles the wire leveling and address remapping. There's an AIT data buffer stored in on-DIMM DRAM, which we refer to as L2 buffer in the previous slides. And finally, there is a media model to simulate the non-volatile memory media. WANS also provides a powerful and easy-to-use testing framework to help the users verify their model accuracy. The user can define a test with a simple configuration file. Then, the testing framework automatically generates a set of memory trace files according to the configuration file and run the simulation in parallel. After all tests are finished, the framework automatically collects all the results and generates a report. Here's an example report generated by the testing framework. It shows performance comparison between simulation and obtained DIMM, and plot all the internal hardware counters inside the WANS simulation. More importantly, all these testings are automated. The user just needs to set up a configuration file and then use this one line of Python command to run the tests. We believe this helps users to quickly develop their own non-volatile memory system model. Now, let's take a look at the validation results. We verified the WANS DDR4 model using Micron DDR4 verification model with Cadence toolchain. For non-volatile memory model, there is no formal verification tool, so we match the micro benchmark performance on the obtained DIMM. Here are the validation results using pointer tracing micro benchmark on single DIMM and interleave 6 DIMMs. We notice the WANS latency numbers and curves match the obtained DIMM very well. We also take the hardware counters from obtained DIMM and WANS to calculate the rate amplification for L1 buffer. As shown in the left figure, the amplification factors match very well. We then perform the override test on WANS and find its long tail latency match the obtained DIMM. In summary, we first build Lens Profiler. It contains a set of customized micro benchmarks and use them to discover the complex microarchitecture design of non-volatile memory products. Based on lens profiling, we build WANS, a non-volatile memory simulator that matches Intel obtained persistent memory DIMM's performance. It contains verified DDR4 model and validated non-volatile memory model, and can be integrated to Gem5 or other cycle-level simulator for full system simulation. Lens and WANS are now open sourced on GitHub. This is our project, Characterizing and Modeling Non-Volatile Memory Systems. It is initially published on Micro 2020 and recently selected by IEEE Micro Topics. Due to the time limit, we cannot present all the details. For more information, please read the paper and check our code on GitHub. Thank you.